The idea of a limit is the key foundational concept that distinguishes calculus from algebra. This is part one of some problem solving with limits and continuity. We start with the problem where we are given the graph of a function f as shown below. Part A says to find all values of x for which this function f is not continuous. Okay, so we want to think intuitively at the start and then relate this to limits. Intuitively, a function is continuous over its entire domain if you can draw its graph without picking up your writing utensil. So, where a function fails to be continuous is where you have to pick up your writing utensil. So we look at this graph and we see that, try to imagine drawing this, and we see that there are two spots, two values of x for which you'd have to pick up your writing utensil at x equals -1 and at x equals +1. So the answer to part A is that x equals -1 plus or minus 1 are the two values of x for which f is not continuous. That's the answer for part A. This is where f is not continuous. So evidently then, that means it's continuous everywhere else. And part B says to find the largest open intervals on which f is continuous. Now, these open intervals in this particular picture happen to have the same length. However, if you had a problem where they had different lengths, I think the author of the textbook probably would want you to write down all open intervals on which f is continuous. So for example, it's continuous from -3 to -1, certainly not including the endpoint -1. There is no open circle here at -3, but they do say make the answer an open interval, so we'll go ahead and use open interval notation. Also from -1 to +1, and then from +1 to +3. So in terms of answering the question as it is phrased, I'll go ahead and use interval notation to start with. For example, -3 to -1, that looks like a point, but it's actually an interval. If you use set builder notation, you'd say this is the set of all x with the property that x is strictly between -3 and -1. Either kind of notation is fine. The next interval again goes from -1 to +1. So you could use open interval notation or set builder notation like this. And the third open interval is from 1 to 3. We're using open interval notation with parentheses instead of square brackets, saying we're not including the endpoints. Again, because of how the problem is phrased. In this particular graph, again, there's no open circles here or here, so technically you could include those endpoints as part of the domain in which f is continuous, but the problem says open intervals, okay? So we'll go ahead and go with that. Part C. Find all values for the following limits if they exist. If the limit does not exist, say so, okay? So take these one at a time. Number one, the limit as x approaches -2 of f of x. Does that limit exist, and can we find its value? Okay, so this may be a new concept for you. What we're after is we are after the output values of f of x. What are they getting closer and closer to as x gets closer and closer to -2 without actually equaling -2? That's where the biggest confusion comes into play, especially when we relate it to continuity, because we're ultimately, in this particular example, going to think about the function value at -2. So it is a really confusing concept that way, but it is key to fully understanding what calculus is about. So x is approaching -2, so I imagine x getting closer and closer to -2, either from the right or from the left. The function outputs, which are the second coordinates of these points on this graph, are getting closer and closer to 0. Do they equal 0? Not unless x actually equals -2. They don't. But they are getting closer and closer to 0, closer and closer enough that we can say that that limit does exist. The limit, okay, so this is part C, part 1 here. The limit as x approaches -2, again, either from the right or from the left, of this function, that limit does exist and does equal 0. Okay? Say it again. The function values as x gets closer and closer to -2 without actually equaling -2 are the second coordinates of these points on this graph, they are getting closer and closer to 0. Their y values are getting closer and closer to 0 without actually equaling 0 unless x actually equals -2. We can make them as close to 0 as we like if we make x close to -2. Now, again, the function value at -2 actually is 0. And that's related to the fact that this function is continuous at -2. But the more important thing is the function values get arbitrarily close to 0 as x gets close enough to -2. And that's what makes this limit 0. It's a very, very subtle concept. Let's go on to the second one of part C. The limit as x approaches -1 of f of x. Okay, this is where this subtle concept is really going to come into play, because the function is not continuous at -1. So is the limit the second coordinate of that missing point of the graph, or is it the second coordinate of that point? Maybe you want to pause the video and think about it. The limit as x approaches -1 of the function. So once again, x is getting closer and closer to -1, either from the right or from the left, without actually equaling -1. What are the function outputs getting arbitrarily close to? Let's think about the second coordinates of these points on the graph here and here. They are getting closer and closer to 1, not 2. This limit does exist and equals 1. And it doesn't matter that the function value at -1 is actually 2. That is completely irrelevant for the value of the limit. This limit over here happened to equal the function value at -2. And this limit right here does not equal the function value at -1. What's the difference? Why did it work there and not there? Because here at -2, the function is continuous. But at -1, the function is not continuous. So the fact that these two things are not equal is related to the fact that the function is not continuous at x equals -1. Making these key points here. All right, on to the next part, part 3. The limit as x approaches 0 of f of x. Limit as x approaches 0 of f of x. So now we're letting x get closer and closer to 0 without actually equaling 0. The function values, the second coordinates of these points, their y values, are getting closer and closer to -1. And it doesn't matter that this graph has what you might call a corner in it. It's not smooth when x equals 0. That's completely irrelevant for the value of the limit. Does look like the function value does equal -1. There's no open circle there. This is equal to -1, and that does equal the function value when x equals 0. The function is continuous at x equals 0. And it's, again, completely irrelevant for continuity, the fact that there's a corner there. It's not completely irrelevant for derivatives, for something called differentiability, but that's a later topic. On to the fourth part here of part C. Fourth part, looking over here. The limit as x approaches 1. What's this minus sign there? Should that be in front? Is that a typo? No, it's not a typo. We are letting x approach 1 from the left. This negative sign does not mean negative number. It means from the left. This is weird notation, but it is standard notation. We're letting x approach 1 from the left, not from the right. Let x be 0.5, then 0.9, then 0.99, then 0.999. What are the function values approach? The second coordinates of these points are approaching 1, which is the second coordinate of that point. The limit as x approaches 1 from the left, second coordinate of the missing point, I should say, does exist and does equal the second coordinate of the missing point, 1. The function never equals 1, okay, over here. The function output is never equal to 1. It just gets arbitrarily close to 1, really close as I like, by making x sufficiently close to 1 on the left. That means this one-sided limit does exist and does equal 1, but that's not the same as the function value when x equals 1. The function is not continuous at 1. There's a jump in the graph. Okay, so we're seeing, again, the relationship between continuity and limits here. Part 5, we're letting x approach 1. There's a plus sign there. That means from the right. Not necessarily through positive values, though of course numbers that are bigger than 1 are positive. But from the right, we're letting x approach 1 from the right. The function values are up here now. They're getting closer and closer to 2. For that one, the limit as x approaches 1 from the right does exist and equals 2, not 1. This is also a one-sided limit. There's other names for these things. This one where we're letting x approach 1 from the left is also called a left-hand limit, and this one where we're letting x approach 1 from the right is called a right-hand limit. I'll just leave it as is, the labeling. That does happen to equal the function value when x equals 1. But that's not enough to say f is continuous at 1 because this one-sided limit did not equal the function value. And these two things, in part 4 and 5, giving different answers, 1 and 2, is enough to say that for part 6, the limit does not exist. The two-sided limit, where you don't see a minus sign or plus sign to the right of the number, does not exist because the one-sided limits, even though they exist, they're not equal to each other. For the two-sided limit to exist, both one-sided limits must exist and equal each other. So this limit here does not exist. DNE is a standard shorthand for does not exist. Okay, and the reason is because the one-sided limits are not equal to each other. And this limit not existing means it also can't equal f of 1. So that's another reason that the function is not continuous at 1. You could say, this is a little funny, you could say the function is right continuous at 1 because the right-hand limit does equal the function value. There would also be a corresponding concept of left continuous, but we're not going to go there. It's just not continuous. And the last part, the limit as x approaches 2 of the function. Part 7 here. Now we're letting x approach 2 from the left or right. It's a two-sided limit. X approaches 2. What do the function outputs get close to? They get close to the second coordinate of the point here, which would be 3. And that does equal the function value at 2. This function is continuous at 2. Number 2 is easier than number 1. Let f of x be 1 divided by the square root of 3x minus 9. The goal is to find the largest interval over which f is continuous. It's implicit in a problem like this that you're allowing yourself to plug in any value of x for which this function makes sense. It's also implicit in a calculus class that we're not going to take square roots of negative numbers, so we don't want to get complex non-real number outputs. Okay, that's also implicit in a calculus class, which I'm assuming you are taking when you watch this. So what do? It turns out that for functions like this, which are either rational functions, which are ratios of polynomials, or things involving square roots, where we want to avoid taking square roots of negative numbers, and we also want to avoid dividing by 0. And that's the key insight. This function will be continuous, in fact, wherever it's defined and not equal to some non-real number. Okay, you can also use your graph to figure it out, but we can figure it out without a graphing calculator. You want to, again, avoid dividing by 0, so you don't want 3x minus 9 to equal 0. You also don't want it to be negative. You want it to be positive. So we need to solve this inequality effectively. It's equivalent to saying, by adding 9 to both sides, that 3x is bigger than 9. And that's equivalent to saying, by dividing both sides by 3, that x is bigger than 3. So the largest interval on which this function is continuous could be written in interval notation as the open interval from 3 to infinity. Again, it's an open interval. I'm not using a square bracket there. I'm not including that endpoint. And in set builder notation, that would be the set of all real numbers x such that x is bigger than 3. Either kind of notation is fine. If you wanted to draw it on a number line, you'd mark the number 3 here, and you'd make an open circle there, and then shade everything to the right of 3. That's the domain of the function. It's also going to be the set where the function is continuous. If you graph this with your technology here, what will we see? I hope you can kind of predict what you're going to see to some degree. You are dividing by something that gets close to 0 as x gets close to 3. In fact, that means the output of this is going to get very, very large, go off to infinity, you might say, as x gets close to 3 from the right. And then, as x gets big, it's going to go down towards 0. So you should see some kind of decreasing graph with a vertical asymptote and also a horizontal asymptote. 3x minus 9. If on my window screen, if I just keep it, say, this window, I don't think we'll get an error. I think it'll graph it, but it will only start the graph once we get to x equals 3. There it is over there, just this little piece. It doesn't look like it's a vertical asymptote, but it should be. It's just maybe not plotting enough points here. Let's start it at 3. See if we see any more. Yeah, it's hard to see. I mean, if we plotted it really close to, say, 3.5 here or something, let's see if we see any more detail. Yeah, you can see it is going up fairly rapidly as your x approaches 3 from the right. Yes, it actually is a vertical asymptote, even though it doesn't quite look like it. It's a case where your technology could be misleading you. As x approaches 3 from the right, the value of 3x minus 9 is approaching 0. The square root of something approaches 0 is also approaches 0, meaning this fraction is getting very large. It's 1 over something very, very close to 0. It's going off to infinity. It's not a proof, but that is what's going on in this problem. Problem number 3 is about continuity in an applied problem. A 0.8 milliliter dose of a drug is injected into a patient steadily for half a second. So there it's like they're getting injected with a needle here. At the end of this time, that half second, the quantity Q of the drug in the body starts to decay exponentially at what's called a continuous rate of 0.1% per second. Okay? You might wonder, is this something that could actually happen? Don't worry about it. If this is mathematical modeling, it's not going to be perfect. We just want a decent model. Using formulas, the goal is to express Q, this quantity, as a continuous function of time t in seconds. Seems pretty hard. It's probably best to try to draw a reasonable graph first for Q as a function of t. So the horizontal axis is t, time in seconds, and the vertical axis is Q, the quantity in milliliters. Other kinds of units could have been like milligrams or something like that. All right, how do you deal with this? How do you even draw a graph? Going in steadily means the rate at which it's going into your body is constant. It's like walking at a constant rate. For that first half second from time 0 to time 0.5, the graph has got to be a straight line. Going from 0, you don't have any drug right away, to 0.8. Like this. Okay, that's the fact that it's going in your body steadily for half a second. What would the slope of this be? Rise over run, 0.8 divided by 0.5 would be 1.6. 1.6 milliliters per second would be the slope of that line. Then, right away, the instant they stop injecting it, it starts to decay exponentially at a continuous rate of 0.1% per second. Exponential decay graphs look like that. They're decreasing but still concave up. And you want this to be a continuous function, which makes good intuitive sense for real life. You don't want there to be some sort of jump discontinuity in the amount of drug. That wouldn't make any intuitive sense. So you're going to get a graph going down about like this. It's got the t-axis is a horizontal asymptote. There is an exponential decay kind of graph. All right, so that's helpful, I think, to writing the formula. Now the directions say using formulas. The plural there is really referring to the fact that this is going to have to be a piecewise formula. We need two formulas for the two pieces of the graph. One when t is between 0 and 0.5, and one when t is bigger than 0.5. And again, slope of this is 1.6, so, and it goes through 0, 0. So the formula for that first piece is going to be 1.6 t When t is between 0, I'm including 0, and 0.5. Should I include 0.5 in this piece of the formula or not? The answer is that it doesn't matter, at least if you design your formula to be continuous like this. I could put a less than there. I could also put a less than or equal to. I think I'll put a less than or equal to, okay? But it could be either way. Either answer is okay. The exponential decay part, that's a little trickier. It's also made a little trickier by the fact that we're starting at time 0.5 here instead of time 0 for that part of the formula. The initial value at that time, and when I say initial, I mean time 0.5, is the 0.8. So I want a 0.8 in front. The fact that it's a continuous rate instead of, say, an actual rate per second means we need e, the number e, as the base of our exponential function. If it were an actual rate of 0.1% per second, it's a little trickier. You'd need like a base of, in that case, like 0.999. But here we need e because it's said to be a continuous rate. And it's going to be exponential decay, so I need a negative sign here. And 0.1% per second means the coefficient of t needs to be negative 0.001, then times t. Careful though, not just times t, times the quantity involving t, that is 0 when time is 0.5. And it's not going to be a t, that's going to be a t minus 0.5. There's a linear function of t that is 0 when t equals 0.5 up here in the exponent of the e. It's going to get multiplied by negative 0.001. And this is for t greater than 0.5, though I could put a strict less than there and a greater than or equal to there, and it'd be the same function. And this is a continuous graph. As t approaches, we can write down left hand and right hand limits here. Limit as t approaches 0.5 from the left of this function, I can use the formula in that case, 1.6 times t. That's the same as the limit as t approaches 0.5 from the left of 1.6 times t. That's a continuous expression of t. I can just plug in 0.5 and get 0.8. So that's the left-hand limit. The right-hand limit, as t approaches 0.5 from the right, put a plus sign here. We need the other formula because that's the formula that is relevant when t is bigger than 0.5. All right, and even though it's complicated looking, it's a fairly simple limit. As t gets closer and closer to 0.5, this expression up here is getting closer and closer to 0. E to something getting closer and closer to 0 gets closer and closer to 1. 0.8 times something closer and closer to 1 gets closer and closer to 0.8. So these two limits are the same, these one-sided limits. Therefore, the two-sided limits also exists and equals that same number, 0.8, and that is the function value at 0.5. This is certainly a continuous function at 0.5 and in fact everywhere. In problem 4, we are given a piecewise function and we're trying to estimate a limit numerically based on using our technology. The function f of x equals e to the 2x minus 1 all over x if x is non-zero, and is equal to c if x equals 0. Now there might be some confusion here going on in your mind. You might be looking at that formula and saying, how can the limit as x approaches 0 if this thing exists? Wouldn't this have a vertical asymptote? And amazingly, it doesn't. That's a pretty important thing actually for calculus. Part A says to make a table of values of f of x for values of x that are close to 0. Negative 0.1, negative 0.01, positive 0.01, positive 0.1. Actually, we'll use the table feature on our calculator to look at the values of this for more values other than just these, but those are the ones that we'll write down. We're ultimately going to use the table to estimate the value of the limit, which evidently exists based on the way this problem is phrased. And then we're going to ask in part C, what value of the constant c will make the function f continuous at x equals 0? I won't say the answer right now, but I hope you realize what to do for part C based on the previous problems that we've done. So in part A, we'll go ahead and write down a little table on the paper here. for these values of x, negative 0.1, negative 0.01, positive 0.01, and positive 0.1. I'll go ahead and do, say, this one with a calculator by plugging numbers in, but then we'll use the graphing feature where we can actually make a table as well to do it more quickly. So we can just do it step by step. When we plug in negative 0.1 here, we first find e to the negative 2 times 0.1, or 2 times negative 0.1, which would be e to the negative 0.2, subtract 1, and then divide by negative 0.1. Divide by negative 0.1. We get about 1.8. Okay, let's go 1.81 is what that is. Okay, and I could do that for the other ones as well. I could also do it all at once. Let's just double check it that way. I could do e to the negative 0.2 and then minus 1 divided by negative 0.1. Yep, about 1.81. Okay, let's use the table feature in the graphing calculator portion. I'll plug the function in here. So again, it's e to the, looking at the formula up here, 2x, 2 times x, and then minus 1, all divided by x. And let's now make sure our table settings are good. I'd want to start at negative 0.1 and do the delta table to be 0.01. And let's see what we see when we make the table now. So this first value of y, that's the one I wrote down. Going down the table, there's the next one I want, 1.98. I get an error when x equals 0 because the calculator is trying to divide by 0. That's an error. How about positive 0.01? I get 2.02. And positive 0.1 looks like 2.21. So as x gets closer and closer to 0, as you move toward the center of the table, so to speak, what are these outputs getting closer and closer to? Well, they're pretty close to 2. Let's go ahead and assume that that is the limit. Now, is that a good assumption? It does turn out to be the right answer here. For the true value of the limit as x approaches 0 of this function does in fact equal to 2, but it's no proof, okay? It's just numerical evidence. I suppose we could, if we wanted extra confirmation, go back to our table settings, start at negative 0.01 and make this be 0.001 and see how it looked then. And we get really close to 0 without equaling 0. Yes, the outputs are getting really close to 2. Okay, and in fact, they get closer and closer to 2 as x gets closer and closer to 0. We can make it as close as we wanted to by making x sufficiently close to 0 without actually equaling 0. Okay, at least in this part of the formula. That expression that right there gets arbitrarily close to 2 without actually equaling 2. But the limit is 2. This is something I've been emphasizing already in this video. And that is the answer to part C. For part C, you'd want f of 0, well, okay, for the value of c, yeah, I guess that is part C still. What value of the constant c will make the function continuous at 0? F of 0, which is c, does need to equal 2 to make the function continuous there. Let's go ahead and make a graph of the function as well. Check my window here. Negative, let's do like negative 5 to 5. And then maybe negative 5 to 5 here as well. So there's the function. As far as the calculator is concerned, it looks like the function value when x equals 0 is 2. The calculator technically is just skipping over plugging in 0 to give, it's not giving us any kind of error. It's just plotting points and connecting the dots. It doesn't know that the function, if I did not include the c here, is undefined when x equals 0. All right, so it looks like the limit is 2 graphically as well. That is the answer. Problem 5 is about trying to evaluate certain limits using algebra. And it's kind of a hard problem because you can't just plug in what x is approaching because you'd be dividing by 0. And so again, the intuition is you might think that these functions that you see here, function of x, two functions of h, might have vertical asymptotes at what x or h is approaching. But in this case, this particular problem, these limits actually do exist and equal particular numbers. That's not obvious at all. If these functions happen to be continuous at what x or h was approaching, then you could plug in those values of x or h into the formulas and get the answer. Those would be easy problems. These are harder problems. Part A, evaluate this limit as x approaches -4 of this expression. Now, it's also possible in situations like this that the limit does not exist. Okay, that is possible. But in these particular problems that I picked, the limit does exist. How do you know? In this case, with part A, factor the top. We can factor the top as x plus 4 times x minus 5. And we can simplify this expression, cancel those x plus 4s, and is this valid or not? Can we say the limit as x approaches -4 of this expression is the same as the limit as x approaches -4 of just plain old x minus 5? Is that okay, question mark, to do that? It turns out it is okay, though you can't just do it without thinking about it. These two expressions here and here are equal, and these are both rational functions of x, and they're undefined when x is -4. I'm not doing piecewise formulas here. This expression is defined when x is -4. So how can you do this? These two expressions, here's the key, these two expressions are equal as long as x is not equal to -4. And remember, with limits, in this case, as x approaches -4, either from the left or from the right, it does not actually equal -4. We don't care about what happens to these functions, technically speaking, at -4, when x equals -4. Doesn't matter that that's undefined. The limit could still exist. And this function is a nice simple function. It's a linear function. Its graph is a straight line. It's defined everywhere and continuous everywhere. And I could evaluate the limit of this one by plugging in -4 and get -4 minus 5 is -9. That's no problem. That's continuity. Continuity of the expression of the function x minus 5. Everywhere, it's certainly continuous everywhere. It's also continuous at -4. This thing is okay. The reason is it's irrelevant what happens to this function at -4. This function equals this function when x is not -4. And so if this function has a limit, this one does too. The graph of this function in part A, in either form, is actually a straight line, except with a hole in it. It's a line with a slope of 1 and a y-intercept of -5. When x is -4, technically speaking, the graph of the original function has a hole in it, a point missing, right? When I draw a circle like that, an open circle means a point is missing. That's a little bit misleading because points don't really have any area. That's what's going on. That's the graph of the original function. It's undefined at -4, no vertical asymptote. The limit does exist and equals -9. This function, x minus 5, would fill in that hole, so to speak. This is what's called a removable discontinuity. Similar things happen with B and C. Let's go ahead and just do the algebra without talking about graphs. These kind of limits that you see in B and C are going to come up a lot in calculus with derivatives. So they are worth getting a little practice with. So here's the one for part B. What you want to do is you want to do some algebra first. Expand the top here. You got to do 5 plus h quantity squared, meaning to use FOIL method, 5 plus h times 5 plus h. First times first is 5 times 5 is 25. Outside times outside and inside times inside are both 5h. Add those and get 10h. And then last times last is h times h is h squared. Simplify, the 25s cancel. On the top, we'd like to be able to plug in 0. We can't yet because we'd be dividing by 0, but you can factor out an h out of the top like this. And then, yes, you can divide out the h and say the limit is the limit of this thing. As h approaches 0, this is a continuous function of h. You can just plug in h equals 0 to get 10 plus 0 is 10. Once again, there is the trickiest step to justify. As a function of h, this is undefined at h equals 0, but this is defined at h equals 0. But these are equal as long as h is not 0. So if the limit of this one exists, so will the limit of this one. The limit of that one is definitely 10, therefore the limit of this one must be 10. If you graph this expression as a function of h, it will look like a straight line again with a point missing at h equals 0, just like what happened in part A. Part C. Yikes. There's part C there. What in the world? Letting h approach 0. Can't plug in h equals 0. Fractions within fractions. What in the world am I going to do with this? Let's write it down. There's two, you want to use algebra to simplify it. There's two things you could do here. You could either subtract these fractions right away by getting a common denominator of 4 times 4 plus h, and then divide all that by h, same as multiplying by 1 over h. Or what I find a little quicker is to multiply the top and the bottom of this big fraction by the common denominator, 4 times the quantity 4 plus h. If you do it to the top, you got to do it to the bottom to compensate. So I'm also, that's a little bit messy. So let me redo it over here. Just to be clear about what I'm doing, I'm multiplying both the top and the bottom of the original fraction by the common denominator of the smaller fraction, so to speak, in the numerator of the bigger fraction. Because then when I do this, when I distribute, I'll get cancellation. You know, I'm writing that down, but if you know how to do this in your head, you don't even have to bother writing that down, which is why I think it's a little quicker. But so I get cancellation of the 4 plus h there and just get a 4. Get cancellation of the 4 there and you get a 4 plus h. Careful with parentheses there. I'm subtracting that whole thing. And the bottom becomes more complicated, but that's okay. The top, the 4 is canceled. Distribute the minus sign through. I get the limit as h approaches 0 of negative h divided by 4h times 4 plus h. The negative h and the h can divide out to leave a negative 1 up top. Let me go ahead and write it. Negative 1 over that h divided out, so I have 4 times 4 plus h. And now you can plug in h equals 0 because you're not dividing by 0. This is a continuous function of h at h equals 0. Of course, it's also discontinuous at h equals negative 4, but that's not where we're letting h approach. So I get negative 1 over 4 times 4, negative 1/16 is the limiting value. And by the way, you can check parts B and C with your calculator. If you graph these functions of h, you'll see that these things are right. Our last problem for this video is about what you might call a wild function, sine of 1 over x. We want to intuitively explain why this limit, as x approaches 0, of sine of 1 over x does not exist. Certainly this function is undefined when x equals 0. 1 over 0 is undefined. Can't take the sine of an undefined number. But that doesn't prove that this limit does not exist. The limit still could exist, as we've seen in some examples in this video. It's not clear what's going on here, why this wouldn't necessarily exist. Let's go ahead and use the calculator to see what seems to be happening here. So I'll type sine of 1 over x. You would assume your calculator is in radian mode, which mine is. Though in degree mode, you'd see something somewhat similar. It's assumed everything's in radians here, unless said otherwise. Sine of 1 over x. Let's pick a window. Oh, let's go ahead and keep it like this to start with. Although these are, well, okay, let's make it smaller in the y direction. The outputs values are outputs of sines. They're between negative 1 and 1. negative 1 to 1, and make this maybe 0.1. Let's just see what we see here. Okay, whoa, what in the world's going on there? Something a little strange does seem to be going on near 0. It's almost like it had a vertical asymptote, but then it went back up again, and it sort of oscillated kind of rapidly there. Let's zoom in closer to 0 and see what we see. Oh, something definitely weird going on. You might wonder, is this graph accurate? And I would say to you, actually not necessarily as accurate as could be, at least. Let's try negative 0.1 to positive 0.1. Whoa. Whoa. Okay, first of all, a word of warning. Sometimes when you see graphs like this in problems like this, for different examples, excuse me, it's actually calculator error, okay? And there is some calculator error here going on, especially like in there, for example, that is making this graph not as good as it could be, you might say. However, this function does still behave in a wild way near 0, and that's a graphical reason why the limit as x approaches 0 does not exist. Technically speaking, on any tiny interval near 0, no matter how small, the graph actually oscillates in reality infinitely often. Whoa, does that blow your mind? Infinitely often. But why? Why would that happen? As x approaches 0, let's just say from the right, just to keep it simple. To keep it simple. One over x is getting very, very large, right? If you do 1 over a really small number, it's really big. If x is 0.1, then 1 over x is 10. If x is 0.01, then 1 over x is 100. If x is 0.001, then 1 over x is 1,000. This is getting bigger and bigger. And if I'm letting x approach through positive values, you could say it's approaching plus infinity. I'm not saying infinity is a number. I'm saying 1 over x is getting as large as I like, positively speaking. So the input for the sine function is getting larger and larger without bound, going off to infinity. The ordinary sine function has a graph that looks like this. As its input along the x-axis grows larger and larger, it oscillates between negative 1 and 1 in a periodic way, period 2 pi. And as x goes off to infinity, you could say there are infinitely many oscillations. The sine of this quantity that's going off to infinity has to go through infinitely many oscillations between negative 1 to 1. So you could say, if you're just keeping yourself to an intuitive explanation, you could say that so sine of 1 over x is oscillating infinitely often, and for extra emphasis, between negative 1 and 1, as x approaches 0 from the right. And the same kind of thing would be true as x approaches 0 from the left. If you want a little bit more rigor, you could, for example, ask what values of x will lead to the sine of 1 over x equaling, say, 1 or negative 1 or 0. For example, sine of 1 over x equaling 1 means what? Means the input, where's the sine equal to 1? If you think about the unit circle definition, it's a pi over 2 and go around another 2 pi to, what would it be? Threw it in my head here. 5 pi over 2, and then 9 pi over 2, and then 13 pi over 2. If x is positive here, this means 1 over x would have to be pi over 2 plus some integer multiple of 2 pi, 2n pi, for n equals 0, 1, 2, etc. I could also think about negative values of x, and then I could allow n to be negative. And that would be, if I solve that for x by getting, first of all, say a common denominator here of 2 pi plus 4n pi over 2. I can solve for x by taking the reciprocal of that. 2 over pi, I'll factor out the pi in the bottom, 1 plus 4n. N equals 0, 1, 2, 3, etc. And those numbers are all 2 over pi or less. As n gets bigger and bigger, these numbers get smaller and smaller. When n is 0, it equals 2 over pi. On a number line, if 0 is here, 2 over pi, you know, is a little less than 1. If 1's right there, 2 over pi might be right there. And then when n is 1, it would be 2 over 5 pi, I guess. It'd be right there, 2 over 5 pi. Then it'd be 2 over 9 pi, then 2 over 13 pi, etc. These numbers get closer and closer to 0, and at all those numbers, the function output equals 1. And for it equaling negative 1, that means 1 over x is going to be, let's see, down at negative 1, it'd be 3 pi over 2 plus 2n pi. N equals 0, 1, 2, 3, etc. Get a common denominator of 2. This is 3 pi plus 4n pi all over 2. And we could solve that for x. 2 over, again, I'll factor out the pi. Pi times, in parentheses, 2 plus 4n. N equals 0, 1, 2, 3, etc. And these are all numbers that are not equal to these numbers, but are still behaving in a similar way, going towards 0. And there's infinitely many of them. So, you know, there is some algebra that you'd want to add that kind of explanation to help you finish the problem if your teacher is looking for a little bit more explanation than just what I had up here, to intuitively explain why this limit does not exist. The function is oscillating infinitely often with a constant amplitude of 1 between negative 1 and 1 as you approach 0. On any tiny little interval around 0, the function oscillates infinitely often between negative 1 and 1. There's no way for this limit to exist. Thanks for watching.